All right, today we're going to see these very interesting devices called the operational amplifiers. And let's try to understand them, uh, what they do, and what the mathematical representation of the symbols are. So on the screen, you have the basic operational amplifier, um, which is a device that is actually externally powered. And what it is supposed to do? This is an electronic amplifier used to implement transfer functions. So maybe what I should do is, well, I'll just make a little definition. We're going to call it their electronic device used to implement transfer functions and other purposes. Then we are also going to say that this is a device that is um, externally powered, and we are going to say that in here you see you have an input in here, you have a voltage difference between this and this end. So the idea is to be able to amplify. This is the voltage output. So the idea is to be able to create the voltage difference between these two, and then the output is going to be amplified to become this. So we are going to first say this is a differential input. Let's write it down. I'm gonna have to get input. Okay, differential input. So B sub 2 of t minus B sub 1, or B sub 1 of t is going to be the differential input in there. The other characteristic of this example is that it has a high input impedance. Yeah, we're going to expand a little bit more on this concept of impedance. We use the letter Z, Zi. This is very big, infinitely big. The characteristic is that for the output, low output impedance. Okay, so that's for the output. And the other characteristic is it has a high constant gain. And this is the gain. In this case, we use the letter A for the amplifier in there. What I think is important is to realize that the way we have it here is that the output voltage B out of T is going to be equal to the input voltage times this amplification factor, which would be V sub 2 of T minus V1 of T. right? So this is how we define the output in here. Now, let's talk about a little bit about the concept of impedance here. I'm just gonna put the title here. Let's go down here. Impedance. If I can use the word instead of impedance, the word resistance may actually work too, because for a resistor, you know, for an element that is like an element that is for a resistor, you know, like you have this kind of element like this. Isn't it true you have the current I, and then you write that the voltage across the resistor is equal to the current times the resistance, right? This we say times resistance. So this one is very obvious. So Z for this element, Z is actually R. The impedance is R. But let's say we change. We have now this capacitor here. Okay? And you have the current I circulating here. What is the voltage across the capacitor? This is 1 over C times the integral of I dt, right? But in the Laplace domain, like B C of S, is 1 over C times 1 over S I of S. So for this, the impedance for this particular example, Z of the capacitor is going to be 1 over CS. And if you have the inductor here, you have an inductor here. If you have an inductor, you know that the voltage of the inductor is equal to L, you know, if this is L, this is C here, times the IDT, right? That's the way we define it. So in the Laplace domain, the voltage across the inductor, let's just, instead of V sub I, put a V sub L, across the inductor is going to be L times S times I of S. So the impedance for this device is going to be S. See, this is why I am trying to say is, S L times S, excuse me. What I'm trying to say is for these devices, you can write it also in terms as if they would be resistors, see? So now let's talk a little bit more about the operational amplifier as you see it in this example, so that we can do a little bit more of an analysis here. So in here you have that this is the, let's just analyze the system first. So you have here the input, and you have the operational amplifier here. This is the output. In this particular case, what you want is that this current here is 0. So it's made in such a way that this current is 0, so that you amplify just the voltage. Voltage would be V sub 1 times A. It would be the output voltage. So let's write down the equations for this operational amplifier. So the very first one is you're going to say that the output of this is going to be equal to minus A times B sub 1 of t. Now, on this, in this corner here, you see, maybe I'll just do it so that we don't, we understand each other really well. Let's say you have right here, you have I2 that comes this way, right? You have that from here you have the other current, which would be I sub 1. Yeah. And what goes in here? This would be I sub A. But this is what we want it to be 0. So if this is true, based on what I just did, if this is true, then it follows that because of Kirchhoff's laws and the law of the nodes, so that I sub 1 plus I sub 2 of S would be I sub A. But if I sub A is 0, consequently it means that I1 of S is minus I2 of S. Okay, so this is what is called an inverting operational amplifier. So you could write down from here that if you have the if you equate this, like you have I1 of S equals to minus I sub 2. So you could actually write this I1 of S is equal to V sub 1 over Z1. See, this comes from this very basic concept, see? So the current is voltage over the impedance, okay? So this is the, like I say, this R is the impedance here. Impedance, I'm gonna write it down. It's the impedance concept in here. So now that we have established that this is like this, then it follows that I sub I is minus I sub 2, which would be you have minus I sub 1 of S is going to be equal to, no, minus I sub 2. This would be minus V sub 0 S over Z2. Okay, once we have this, you understand that V1 of S over Z1 of S would be minus B output of S divided by Z2. So, for consequently, you say therefore, the output B of S is going to be equal to minus Z2 over Z1. All right. So this is why you could see the and this times B1 of S. This is why it's called the inverting operational amplifier. So you will see the results for this particular circuit. As you can see, the circuit that we were looking at the top, this one is an inverting operational amplifier. And this equation proves that the output voltage depends on a ratio of the two impedances and the input voltage. That is the definition of this operational amplifier. We call it inverting operational amplifier.